My name is Kyle Simmons, and I am a junior investigator here at the Laureate Institute for Brain Research. So my research primarily involves using functional magnetic resonance imaging to study the neural basis of cognition. In particular, my work here is focusing on using fMRI to develop a better understanding of the neural basis of eating disorders, particularly anorexia and bulimia, with sort of a long-term goal of, again, understanding the biological basis of these disorders, but in particular defining and finding biomarkers for the disorders that we can use to predict things like treatment outcome and what sort of treatment is going to work best, and who's going to respond to treatment, that sort of thing. Functional magnetic resonance imaging, or fMRI, is sort of the primary tool that we're going to be using here at LIBR. And basically what this involves is putting a subject inside the MRI scanner and having them perform cognitive tasks while we look at changes in the ratio of oxygenated to deoxygenated hemoglobin in specific brain regions. And so what we can do with those scans is that we can then look at the relationship between those changes and the task that we have the subject perform, and we can begin to produce sort of statistical maps, kind of like these you see on the screen here, that show us the involvement or some measure of the involvement of a particular brain region in a particular sort of cognitive state, and then compare that activity between, say, patients and control subjects, or say between patients with anorexia nervosa and healthy sort of age-matched controls. I guess one of the major challenges to this type of research is actually sort of just data management. I mean, these scans produce a lot of data for each individual subject, and then of course once you start doing the analyses, you have all these hundreds of processing stages, and for every single stage you've got more and more data sort of compounding, and very quickly when you've got lots of subjects and lots of different patient groups and lots of different tasks and lots of different types of scans and lots of processing stages, you end up with very, very large data sets. And so one of the major challenges here, and one of the things that we're working with the computer science people here with, is ways to sort of streamline that and to sort of create workflows, data flows for hopefully automating some of these analysis steps. So I don't know, any other?
So once you get data from a scanner,
yeah.
Once you get that data, what do you do with it? Like, how do you manipulate that data?
Yeah, so when those data come from the scanner, they're usually in what's called DICOM format, which is a specific type of medical imaging format. And one of the very first things we do is actually pull that data from DICOM format into a different file format that is the particular type of software that we use for data analysis. In this case, it's called AFNI. But there's other types of functional neuroimaging analysis packages, things like SPM or Brain Voyager. There's lots of different analyses packages out there. And then we begin sort of a process of first analyzing the data, or I should say, sort of looking at the data visually, literally, to see, hey, do the data look fine? And then doing analyses on the data to sort of determine the data quality. Once we've decided that, hey, these data are of sufficient quality to sort of continue with the analysis, then we begin running a series of AFNI commands, most of which are actually incorporated in like Unix scripts. And so you have these long scripts of analysis commands where at each stage it creates a new version of the file that maybe it takes the data and it trims off certain time points, and then the next stage it will smooth the data, apply a smoothing kernel to the data to sort of improve the signal-to noise quality of the images. And then eventually, sort of down the road, we'll end up starting to do statistical analyses, things like multivariate regression analysis or deconvolution analysis, for example, to sort of look at the relationship between the changes in the images over time, the brain images over time, and what we had the subject, what we recorded the subject doing in the scanner, or asked the subject to do in the scanner. Does that sort of get it?
Yeah. Yeah, very much so. What do you think is your biggest challenge, with this new institution, this new sort of research thrust?
Yeah.
What is going to be hardest for us to tackle?
I think very quickly we're going to be just awash in files, in data, right? Just gigabytes and gigabytes and gigabytes and terabytes of data, of images. And we're going to, it's never the case that the first time you analyze the data set, that's the end of the story, right? Inevitably what happens is you do an analysis which produces large amounts of more data, and then you realize, well, hey, we need to actually do this analysis in a slightly different way to get at this other question. So now we got to redo the analysis again, but we don't want to delete those other analyses. So everything starts to pile up. Keeping track of all of those data is a non-trivial problem. Organizing it in a fashion so that you can get to it easily and remember what you did, what the characteristics of those data are, how, sort of tagging the data with meta information that tells you what you did to it, and keeping it flexible, keeping that file system and the data access flexible enough so that you can really do the business of science of sort of exploration, right? I mean, one of the things we hope to do is by collecting more, large data sets and large collections of subjects, is that we might be able to use more powerful statistical techniques to begin to address some of the questions that in the past we weren't able to do, because typically imaging studies have used very few subjects, maybe 10, 12, 15 subjects in an entire study, and here we may be talking about a lot more than that.
Hopefully. So when you get like a 10 or 12 person study, just how many man hours, months does it take?
Now you're going to make me depressed. It totally varies from study to study. I mean, some studies are more complicated. I mean, in terms of, I'll put it like this. It is not at all unusual to collect, in this field, to collect the data for a study in a couple of weeks and to spend 2 years analyzing it.
Wow, I didn't even know that.
Yeah.
That's kind of terrifying.
Yeah. It is not unusual to do that. I know people who are, I'm thinking of a particular colleague who's actually working with a data set that is, I'm just convinced, is a fantastic data set. He's written it up, he actually just submitted it for publication, but these data were collected about the time I began my postdoc. We're talking, 4 years ago.
Wow.
And I would not describe that as, while that's a long time, I wouldn't describe it as an undue sort of duration. It's just taken that long to sort of conceptualize what's going on in those data, and to make sense to actually, in his case, to actually develop the analysis techniques necessary to sort of pull out those patterns.
Okay.
Is that something where better, faster computation?
It helps. Yeah. Well, yeah. No, this is a place where it has already helped tremendously, right, in our field. So, a colleague of mine was telling me a story about. So he happened to be at the place where they did some of the first fMRI studies. This was back in like I guess it was in the late 90s, and he was telling me that about somebody who did an analysis that currently you could probably do in a couple of minutes, right? Maybe like 15, 20 minutes of processing time, on a pretty standard computer today. And how he started the analysis and let it run, I think they let it run overnight, or maybe it was like 20 hours. And then right when it was ready to, the program's going to write out the output file, it crashed. And the reason why it crashed was because there was already a file with that name,
Oh.
right? And so, right? So now what they're going to do is they go in and they change the code so that it checks before it does anything to see if there's an output file, file already in the directory with that output name. But of course, right there, so now we have to rerun the analysis. It takes 40 hours, right, with one little glitch to do an analysis that now we can do in minutes. So that has tremendously helped just the horsepower, the processing speed has helped tremendously, and faster disks, the ability to access data faster has helped a lot.
To completely put you on the spot,
Yeah.
what's the as a computer science perspective, what's the best thing that I could do to help you with your data analysis?
Yeah, I can answer that. Developing ways to robustly, and I want to emphasize robustly automate these analyses, right? So that I could take a patient to the scanner, scan them, come back here, and the system, have maybe press, type in a few things over the scanner to sort of initiate, those data into this workflow, this pipeline, processing pipeline, and come back over here, and this thing is, the computer is already running, doing all the pre-processing. It has, algorithms for checking the data quality, right? There are some things that will probably obviously still need to be sort of, eyeballed. There always will be. You always have to eyeball your data, always. But anything that can sort of speed that process of pipelining data, so that because we know there are certain analyses that we're going to want to do from the outset, so that they get scanned and then it's just an automatic thing. The data are pulled into that pipeline and into the various analysis bins, and those analyses run. So that instead of having to sit and write code for a few hours for for each particular study, right, to sort of change things for so that it's particular for the study, at least having a certain core group of analyses that are sort of automated, and that would be a big help.
I think we've talked about that.
Yeah.
We're going to work on that.
Yeah, it would be very, very cool, and it would be useful. There are folks who are already trying to do this in other places, but and there's probably a certain amount of sort of site specificity, right? So it's specific for certain sites and certain types of patient groups that you're working with, that sort of thing. But there's other groups that are trying to do that, but having that would just speed things up a lot. Yeah. Anything else? All right.
I learned.
Good.